Hello, Assalamualaikum. A very good afternoon to everyone. Can you hear me? Oh, you can hear me, yeah? Okay, can you still hear me?
Yes.
All right. All right, Alhamdulillah. Okay, so without further ado, we will start our class. Please switch on your camera and microphone. We will recite our dua. Can someone please prepare as pembuka and penutup?
اللهم صل على محمد وعلى ال محمد اللهم اغفر لنا ذنوبنا ولوالدينا وارحمهما كما ربيانا صغيرا.
So let's read the dua together. Allahumma ja'alni fi qalbi nura
وفي
wa fi
لساني
lisani nura
وفي
wa fi
بصري
basari nura wa fi sam'i nura
وعين
wa ayni nura wa ayyasati nura
ومن
wa
فوق
min nura wa min tuhti nura
ومن أمامي نورا
wa ja'alni fi nafsi nura
واجعل
Rabbish rafli sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Allahumma aftah alaina hikmataka wa anshur alaina min khazaini rahmatika ya arhamar rahimin.
سبحان ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
Amin amin ya rabbal alamin. Thank you to Mr. Akasha.
Thank you, Dr.
You're welcome. Thank you to you. All right, so I will share my PowerPoint slide, and I'm sure that you have downloaded the same materials from class materials.
Yes.
Yes, very good. Okay, I'm sharing now. Sekejap, mata saya lagging sikit. Nampak apa? Tetap. Betul. All right, can you see my PowerPoint slide? Lecture chapter 4.
Yes.
All right, very good. So we are going to proceed. This is the continuation of the week 4, topic 4, part 2. Yeah, you can refer to the same slide. And we were talking about the design volume, and this time we will proceed with the plug flow reactor. As you know, the plug flow reactor volume will change as the outlet, so the volume will increase, and what we want to know is the total volume needed to end the stream flowing from the inlet to outlet. So we need to know the total volume. Yeah, in this case, we are going to derive the total volume for the plug flow reactor in the function of the conversion x. But there are a few things that you have to No, especially on the assumptions, which are critically important when we want to simplify the equation, yeah, to the final equation there, which are, as you see from the list of assumptions there, the x changes throughout axial direction. Yeah, definitely we are saying that the x increases, yeah, from the inlet till the end. So x increases, so it changes throughout the axial direction, yeah, as it goes to the end. In axial direction, the r and the c also change. Yeah, same goes to the r and also the c. Yeah, the c is the concentration. So for the reactant will decrease, for the product will increase. And that is second assumption. The third assumption, in radial direction, the r and the c and the x stay constant. So it means at every slice for a very specific position, at that specific position, for example, the x, c, and r stays constant. So at any point at that slice stays constant. It's just that when it goes axially, then it will change. Yeah. So this is what it means. And the FA naught stays constant. So what is entering is a constant value, meaning this one doesn't change. Yeah. It keeps entering at the same molar flow rate. So as usual, we will write our more balanced equation. So we just keep that process, but we will see that from our few slides after this. This is your final equation that you use for a plug flow reactor, which is a flow reactor system, whereby the volume which changes throughout the plug flow reactor depends on the change of the F inside, yeah, throughout axially over the RA. Then we simply open up that equation. What is RA? What is FA? First, when we want to open up the RA, we need to know whether it's a first order, second order, or zero order. That you will do that later. Yeah, this is just a general equation. But the FA equation, we can already, this is FA naught, we can already express the FA, which depends on the FA naught, and also the the change of the molar flow rate based on the conversion. Yeah, because we know along the way the conversion increases, and it depends on the FA naught which comes in here, FA naught times the x, which changes throughout at every point. So FA naught minus FA naught times x. Yeah, x means how much of that reactant being converted into a product. Yeah, based on the feed. So putting that equation in there, simplify. So the dV can be integrated both sides here. So the final equation would be the V2, which comes from the limit from V1 to V2. The V1, of course, refers to X1, V2 refers to X2. And in this case, the V1, which refers to X1, is actually the X at the initial time, yeah, at time equals to 0. So that is 0. V1 is the starting volume there initially, and V2 is X2. So if we choose the end, then it will be the end, right, at any specific time. So that is general. Now, if we know that it is a first order reaction, of course, you add another assumption, which is the first order reaction. So you add the equation for the first order reaction. This is the FA equation. Then you insert the first order reaction and simplify it, rearrange it so that we can get the V. Yeah. In this case, what is new on this slide is, of course, this is an example of an first order reaction, but we are considering what if the initial volumetric flow rate is not constant, whereby the volumetric flow rate is variable. Yeah, in this case, the volumetric flow rate. So you have these plug flow reactors. So of course we have this FA naught there. We have the epsilon. Yeah, epsilon here is referring to the volumetric flow rate, meter cube per hour, and that is initial. It's not this. No, here is not supposed to be initial there. the volumetric flow rate is not equal to initial, all right? Meaning it changes, yeah? The volumetric flow rate changes. Why do we say the volumetric flow rate changes? Maybe we have a phase of change, yeah, change phase. Yeah, if it's gas form, most probably the number of moles changes. So we cannot say it's a constant volumetric flow rate. So therefore, we have to use a specific formula for that case. Yeah, if we refer to our earlier stoichiometric table exercise for a flow reactor system, when the volumetric flow rate is variable, as you see from the next slide, this is what you have seen earlier. For a flow reactor system, when the volumetric flow rate is not fixed to the initial, yeah, so we have an influence of the change, the ratio of pressure, the change of pressure and the change of temperature. So from our stoichiometric table for a variable volume gas flow system, gives us the information that the CA depends on the change of temperature and also the change of pressure, including the epsilon and X and also the CA naught. All right, so we did this earlier. So I'm going to go back to our previous slide. Since we have that information, we realize that the CA in this formula is from the rate constant. Yeah, no, not rate constant, the order of reaction equation. And we are going to substitute the CA there by this whole thing equation, which is shaded in yellow box, the one that you see in the next slide, right? And we are going to simplify this since we have CA naught. So we are going to express the FA naught. So we are writing it in terms of the same parameter. So assumption number 2, FA can be written as CA times the epsilon naught. FA can also be written as FA naught minus FA naught X. Yeah. And now the CA is that equation which you have replaced it to the CA. Then we are going to consider the ratio of the temperature and the pressure. Yeah, it depends on the situation which you are dealing with. If the condition of your plug flow reactor system is set to be in isothermal, then there is no change of temperature. Yeah, there is no change of temperature for that temperature ratio. So therefore, the T is equivalent to the T naught. So therefore, T, right? Because isothermal will give you constant rate, constant, and so on. So that there is no change of temperature. And if the condition is said to be no change of pressure, it's fixed at specific pressure. So this pressure is equivalent to the pressure naught. Then again, this ratio will become 1. So therefore, 1, 1. 1 times 1, 1. All right. So simply simplify that equation, rearrange it, and find V. And of course, when we need to do the integration, you have to identify which are the parameters which are not needed to be integrated because it's simply a constant value. It's mathematically a value, right? In this case, CA naught is a constant value. So you need to take out from the integral range, the limit. So this is basic equation for this condition when the volumetric flow rate is not the same as the initial volumetric flow rate. So do you have any question before I proceed to the next slide?
No, doktor.
Lama juga saya nak kena jadi mannequin hari ni. But anyway, okay. So let's go to the summary of overall. Okay, the end of the topic 4 actually. So you have seen this many times, but I would like to stress on the integral form here because it's related to the upcoming slides. When we talk about integral form, we are going to use that integral definition mathematically. Volume. Yeah, for example, for the plug flow rate, we have this volume which depends on the integral form, whereby you integrate of dx with the limit x into x out. Yeah, of course we have the And in x, what comes in as the starting x to the x out. Okay. And of course, we have changes of r. Then you also integrate the r equation there. So we are going to use this principle whereby the integral of that specific function can be used to help us to find the volume graphically. All right, we are going to use graphical method. Not to say that we are going to use that, but this is one of the way to determine the volume, right? You have seen earlier from our previous week on the volume for the CSTR, simply knowing the X FA naught if you have CSTR with fit in and fit out. Yeah, if it's a batch, then you only have the reactor, no fit in and no fit out. All right. So here, just to refresh, the volume depends on the FA naught there. Then we have X in, X out, and minus RA exit. All right, or out. So this is what we learned the last 4 weeks. This is week 5, huh? All right. Okay, so fast. Now, this is what I mean, yeah? So we are going to use this mathematical understanding, whatever being integrated, with the integral limit. It means that function to the change of the x. Here would be the x-axis, the function that x and y, whatever curve that you get to a specific limit, in this case x to x, and that area under the curve would be the thing that you do, yeah, for the integral. Yeah, you're actually determining the area under the curve. Yeah, so to find the volume, simply knowing the area under the curve times the FA naught, that will give you the volume for the plug flow reactor. So this is what we call as numerical integration method. And for that, simply numerical integration method, it has 4 specific methods. Yeah. The question would be, what is the difference between each of the method? Yeah, we have so many rules there. Trapezoidal rule, 1/3 rule, Simpsons. This is not Bad Simpsons, ya. Simpsons 3/8 rule. Siapa tahu Bad Simpsons? Tahu ke? Saya sebut ni. Tahu ke? Takut.
Tahu.
Numerical.
Numerical.
Apa dia? Kucing? 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 Kucing?
Tahu.
Oh, awak ni buat saya gelap besar. Memanglah saya duk cakap pasal numerical. Itu, ni nama orang yang duk rekod numerical integration method ni. Saya buat lawak tadi. Saya buat lawak, saya sendiri gelap. Simpsons, kartun Simpsons.
Yang kuning-kuning tu.
Tahu okey, betul lah. Betul lah kau faham So maksudnya dunia kita sama. Saya tahu, apa saya tahu, awak tahu. Apa awak tahu, saya tak tahu. Sama ke? Ya, dah merapu dah ni petang-petang ni. So, so we're going to go back to these 4 types of this numerical integration method. Of course, this Mr. Simpson came up with this rule, yeah. We're going to go and look at each of these rules. But what is the difference, yeah? If we, let's say, yeah, I have a question, yeah. When we want to plot our graph, let's say it's a straight line. So it depends on the number of points, right? Let's say if you have your points there, 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 apa you buat? So you ambil yang the most closest, yeah? So the more points that you have, it will give you the most accurate line, yeah, resulted line, right? Betul tak? Betul kan? Do you know that for a very good curved line, at least you need a minimum of 5 points. If you have a line which is straight line, then 1 point sini, 1 point sini, agak-agak dia bagi accurate line ke? Mathematically, yes, definitely. Mathematically or scientifically, of course, the scientific findings minimum mesti 5 point lah. 5 point. Mesti 5 point, 5.6. Kalau you buat 2 je, memanglah tak accurate langsung. So this is what it means. As it goes from method 1, 2, 3, 4, then the number of point increases. So that is why we have this last method is a 5-point quadrature rule. So out of this 4 rule, the 5-point quadrature rule is the most accurate out of relatively comparing. Yeah, because if you go to the next slide, the trapezoidal rule is only 2 points. If you go to the next slide, 1/3 rule is 3 points. 3/8 rule 4 points, and finally 5 points. Yeah, the 5-point quadrature rule. So let us look at each of the differences between 2 points, 3 points, 4 points, 5 points. Sorry. Now, this is just to understand what the numerical formula solution is for the area under the curve. Yeah, so you have the x-axis, you have you have the y-axis. Sorry, sejuk-sejuk, kau lagi dah ada sejuk dan you batuk sikit ya. So ni kena terapi lain untuk menghilangkan kahak supaya tak batuk supaya semasa mengajar, which I cannot do that now ya. Right. Kalau terbuat tu kira memang berusaha. Tak boleh. Nasib baik pandai. Siapa tu yang suruh tu? Tak apa tu? Tak boleh. Nanti kan saya terbuat kan ya. Payah nanti. Bahaya. Alright. Now, we're going to go back to our 2 point. Kalau 2 point here, how do we, first, we need to know this formula. Yeah, we know that the volume is based on the integral form. And from the integral form, the change of the, based on the limit is the x-axis. Yeah, so we're going to plot the x-axis with the change of conversion. All right. So you have point 1 when the x naught is 0 and the other point at x. Then in the integral, we have 1 over minus RA times the FA. Of course, that is considered outside. So the Fx itself is the whole thing, yeah? In the red circling yang saya buat sini, ya? So FA naught over minus RA, which I write here. That is Fx. So the Fx is the y-axis. So at the point F naught is actually at x naught. F1 is at x1. Why do we write that? Because numerically, for a 2 point, simply the h over 2 open parenthesis, f at the first point plus f at the second point. 2 point. And what is h? H is simply the length from the first x to the other x. All right? And this is happen to be only one segment with the value of h. And that h is simply x1 minus x naught. So to find the volume, once you plot this, so you need to find what is the f at x naught, so which is the y value at x naught and the other y value at x1. Add it up, close parenthesis, times the h over the 2. That will give you your V. Okay? If you plot FA naught over minus RA. So this is what it means by trapezoidal rule, determining the volume numerically. So we still use the graphical method there, the area under the curve with varying x, which is the shaded area, yeah, that one. I don't know why I don't have the shaded area, but maybe I delete it. So that is the shaded area. Now, the 3 points maksudnya 3 points ni lah. 3 points, all right? For a 3-point method, so this 3 points maksudnya x0, x1, x2. And the rule is the segment for each for that point must be divided equally. Meaning, since we divide it equally, so we have two segments, H is equivalent to H. And how do we know the H there? Simply the x2 minus the x0 divides by 2, right? Then it will give you the H. So we have H there. And in the parentheses, we have 3 points. First, the initial, last is the final. The initial is at x0, last is at x2. And the inside is depending on the numerical solution formula, which you can see here. Yeah. So this is taken from the appendix A in your textbook. And it depends on whether we have even number or not even number. In this case, since x0 to x2, then it's an even number. So whatever inside here follows this formula, whereby we have the f0 as the initial, then fn as the final, depending on your n there. And in between, we have still the f at that specific h, but the constant in front changes. Yeah, so it follows the sequence. 4, 2, 4, 2, 4, 2, 4, 2, blah, 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 sampailah hujung. So in this case, since we only need 1 point in between, so it starts with the 4. Okay, only 4. Subset, then final. Initial, final, 4. Times the fx at that middle point, which is x1. Do you have any question before I proceed? Clear? Let's go. So the T pula 3-8 rule, simply 3-8 rule. The previous one is 1/3, 1/3 yeah, times H. So 3-8 rule is a 4 point, so you have 4 points in between. So we have initial, we have final. In between, since we have 4 points, 1, 2, 3, 4. If you divide equally the segment, it will give you 3 segments. Then x3 is a single, not single, it's not even, it's an integer but not even. So it follows this formula, numerical formula sequence of 3, 3, 2, 3, 3, 2. 3, 3, 2, 3, 3, 2 sampailah kat berapa banyak kat tengah tu kan. 3, 3, 2. So since we have since it's a 4 point, so we have point number 1, point number 4, point number 2, point number 3. We need another 2, yeah, value in between at x1 and x2, and the constant in front is 3, 3, 2. So 3, 3. Tak sambung lah tu sebab dah cukup dah. Okay? Alright, do you have any question? No, I think you learned that in your numerical. So the 5 point, the same thing. Since the 5 point, so we have x1, 2, 3, 4, 5. Then the integer is actually an even. So we're gonna go. We are going to follow the sequence of 4, 2. Yeah, 4, 2, 4, 2, 4, 2. Since we have initial, we have final. Since it's 5, so we need 3 points. So 4, 2, 4. Okay. Do you have any question? Now, very good. So this is the summary for the plug flow reactor. Even though some of the summaries we haven't proved it, but we're gonna see it once we do it ourselves with the examples, and it is proven that with the example, with the condition of CSER and PFR for an isothermal reactions, and with the same X and also the same FA0, the volume for the CSTR is greater than the volume for the PFR. Yeah, so we'll have a look at that. But I'm not sure why I don't have that example earlier. Yeah, I'm just checking my flow. I'm not sure why I don't have that, but I'm going to check whether I delete it. But anyway, just bear in mind that the volume for the CSTR is greater than the volume for the PFR. Yeah, I'm actually changing my slide, so jangan terkejut. Yeah. This is valid when we have the same X there and also the same FA0 there. Yeah. So if we compare both, the volume needed to run the reactions achieving the specific X, the same X there, with the same initial molar flow rate would mean that you need a bigger size of CSCR, but with a smaller volume, relatively comparing for if you use PFR. So if your boss asks you which reactor would you choose, opt for, is it CSCR or PFR? If you were to achieve the same X, if you were to achieve the X with the same FA naught. Yeah, if you have two reactors in your chemical plant, but then you may choose whether CSCR or plug flow. So which one would you choose? Nuclear paling lama ni. Which one would you choose? Saya nak kena buat mannequin tak tarik nafas lah. Tutup dong. Nak tengok ni nak jawab cepat ke tak? Sampai hati you, I tak boleh tahan ni. Tak kena nafas.
SCR.
Aduh. Betul lah. Jawab dekat chat box. CSCR ke PFR? Okay, mari kita tengok. Siapa jawab? Penatlah nak buat mannequin tutup hidung. Okay. Lupa pula ada chat box. Jawab. CSCR ke PFR? Bos you tanya. Nak achieve 90%. FA not sama. Saya nak pilih CSCR ke PFR? Okay, jawab. Chat box. Okay, Amani PFR. Karina PFR. Semua? PFR. Oh, lagi kot no. Bahaya buat mannequin tak tarik nafas. Lagging je pasal PFR. 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 Mana pula korang jawab betul ke PFR ni betul? Mari kita tanyalah. Syafiqah, kenapa PFR? Buka video. Nak tengok muka. I wanna see you. Syafiqah. Syafiqah. So why do you choose PFR?
Sebab dia require less dari CSTR.
So?
So maybe in terms of costing ke apa.
Betul lah tu. Kenapa tak yakin? Thank you so much to Syafiqah. Very good. So because of costing, the costing, so it reduce some cost there. You need a smaller, volume. Logically. But maybe we have some other expenses that need to be invested when you go for PFR, you never know, that would be a different case. But at least the basic understanding is there with a lower volume, then maybe the costing might be lower, all right? Theoretically, yes, but we have to prove it, when we have the whole design, with the CSCR and PFR. But it makes sense, for the CSCR, then we have this impeller lah, the motor lah, apa semua. Then of course you have the flow piping, then ada valve lagi, ada pump ke whatever. But the plug flow reactor tak ada impeller, of course if you need pump, then you need pump, the same thing, but you don't have impeller. Dia cuma panjang saja. It's the only critical line tu adakah gives you higher cost, yeah. Instead of one big volume, maybe too big, then maybe you have to divide it into two sets of reactor for CSCR. So what about the cost of the vessel itself in comparison to the pipeline? So it's very subjective on the material that you use. But of course, we have specific rule of using specific materials. Yeah, when you do your design later on in your final year, then you will need to follow through the industrial standards. Yeah, what kind of material that is needed when you are dealing for a specific reaction, especially whether it's corrosive or not, or non-corrosive. Whether it's high pressure or too over pressure or under pressure or vacuum and so on. Right? Very good. Then the point here, we also have that for the CSCR, it's always operated at the lowest reaction rate. Considering this formula, which I go back to my previous summary, yeah, this one, which is depending on the, gimana ni sebab lagging ni tekan laju sangat, tak tahu gimana. Sekejap Allah. Ni. So depending on the lowest reaction rate, yeah, in the reaction mixture, even though it says that out, then it is assumed to be at the lowest reaction rate in the reaction mixture itself. And in the PFR, of course, the PFR starts with the high rate there. You know that the rates changes throughout the PFR. So the R entering is higher than the R leaving, yeah? So the rate of disappearing decreases along the PFR, but the X increases. So this algorithm for an isothermal condition whereby the temperature, operating temperature is constant, is useful if you were to see an overall steps, yeah. For example, here according to the chapters, yeah. So Mr. Pogler just makes it easier for you to, if you were to look into that, so which chapter would you refer to in his textbook, yeah? So we have the flow where more balanced, then the design equation. If you have the rate law, already, then you go to the other path. If you don't have the rate law, of course, you have to determine your rate law. Yeah, that is just to help you. Then the algorithm, the same isothermal condition, it compares between batch, CSCR, and also PFR. So with different condition for the batch, for the CSCR, and also the PFR for a flow or batch system, whether it's liquid, ideal gas, variable flow rate, or variable volume, or liquid with constant volume, or even gas with constant volume, yeah, or volumetric flow rate, yeah, when there is no change of number of moles, even though for a gas form, right? Now, we're going to go to the next few parameters, which are also critical in understanding the plug flow reactor, whereby there are two important different terms for space. We have space time and we have space velocity. So space time is time required to process one reactor volume of feed measured at specific condition. Space velocity is number of reactor volumes of feed at specified condition which can be treated in unit time. The common formula here is tau. Tau is the space time, which is volume over the volume for a specific volume of the mixed flow reactor per volumetric flow rate. Yeah. So if you go to the next slide, it gives you even a better understanding of a space-time. Yeah. For example, here space-time, which is tau, is defined as how much time is needed for that specific volume to be fed full, yeah, in the plug flow reactor. Meaning, if we say the flow rate comes in, then it will start to fill in from point 1 to point B. Let's say at point B, the total volume is 0.2 meter cube. So the question would be, how much time is needed to fill in the liquid full from point A to point B. Yeah? So for example, here we have volume, then we have volumetric flow rate, which you define here. You control your volumetric flow rate, your meter cube per second. You control because you have your control system in allowing only 0.01 meter cube per second. Yeah. So if you use this formula, it gives you 20 seconds. So it means it takes 20 seconds to fill in the whole fluid from point 1 to point B. So that is space-time. But then we have also other intervention for time, name. For batch reactor, we use reaction time, the flux flow, residence time, mixed flow reactor, space time. Yeah, so this is mixed flow reactor, this is flux flow reactor, residence time, batch is reaction time, right? So okay, if you read residence time, yeah, time spent by the particles to reach the desired conversion, of course, reaching certain conversion, depends on what happens in the reactor. TM mean, okay, so time needed to reach certain conversion. Mixed flow, space-time, how much time needed or it takes for the fluid to enter the reactor completely, completely before it flows out. So meaning dia masuk, dia turun sampai satu level baru keluar. Itulah how much time needed to enter the reactor completely. So that is space-time. So now dia macam residence time jugalah, but maybe it does not relate to the conversion, maybe, but for the plug flow then it relates to the conversion, yeah. The residence time, berapa lama dia duduk dalam pipe ni sampai they reach certain X. Yeah, they reach certain X. So that is residence time. In this case, it is said that the space-time and the residence times are interchangeably used, meaning in terms of name, yeah. Sometimes orang guna juga residence time here. Well, it depends on your definition. So that is the only meaning there. So this is what you have seen earlier. Now we're going to go into the different terms that we have LHSV and GHSV. GH relates to the gas hourly space velocity. LH is liquid hourly space velocity. So for the gas hourly space velocity depends on the volumetric flow rate, which is measured at the standard temperature and pressure, STP. This is what you have seen earlier, the simple volume formula for the CSTR. Okay. Then, okay, I'm going to go back. So the volume for the CSTR depends on the FA0 and also the conversion and also the rate of disappearance for the A. Yeah. And now we are also going to express the terms known for the, in this case, we want to write the tau, yeah, the tau in terms of conversion. So how do we do that? The conversion in terms of tau. The other way around also can. Conversion in terms of tau. Knowing the tau, which is the space-time, what is the conversion? So it's simply by simplifying the mole balance equation, which you started with for a CSTR, having the inlet and outlet. Then we use all these assumptions, steady state, the dNA over dt if you are writing the mole balance for the reactant A, which is assumed to be the limiting reactant in this case. So it is considered to be zero there because you assume steady state, yeah, whereby the number of moles of A through time when it reaches steady state is no longer changing. So that is why you write it as equivalent to zero. Then you cancel out there. The second assumption perfectly mixed because you have the impeller. So the R here is constant. So that is why we have the R there. Then there is no, if the volume in the CSR is considered to be constant. So now it becomes RAV for the generated rate of reaction, yeah, in the reactor. Then we have R, so we need to know whether it's first order. So let's say if you assume first order, so that is the equation that you plug in. So that is the first order reaction. then we express the F A naught and F A. What you do is you express the F A. Yeah? So we know equation assumption number 5, F A is that equation. So simply substitute it because you want to simplify the mathematical functions. Yeah, so that you can cancel out the mathematical functions, make it simplified. Then at the denominator we have C, then of course we express the numerator in terms of C as well. So we can express Fa not in terms of C, yeah? C, the concentration. So that would be your equation. Fa naught F is equals to C times volumetric flow rate. Then if the volume is constant, you can also express the CA as that equation. So if the CA there is expressed as that equation due to the volume is considered to be constant, you can use this equation. Then the rest of it, simply simplify it. So now we have the x in the function of tau. If you want to find the x, just simply rearrange it. That is the final equation. Then you could also express from this equation in terms of what is the concentration of A, yeah? Knowing the tau. So this is what it means. All right? So the summary of the topic 4 is shown. I simply made it this way, my own writing, yeah, to compare the batch, the CSCR, and also the PFR. How I wrote the mole balance and how I cancel out, simplify the mole balance equation until the final formula, yeah, based on my assumption. Why I do this is very important, yeah. You don't simply memorize your equation without knowing the origin of writing that equation. So in case if you have that condition, you may never have the same condition in your own chemical plant. Maybe it's a different scenario, but with this basic will help you to write the right equation to solve for that particular parameters. Yeah, if you were to find the volume or the conversion and so on. Go back, gimana? Flip back your notes and understand the simplification of equation by using the assumptions. Okay, so I'm going to give you the first 5 minutes break and we will proceed with the exercise. Right? See you.
Okay, doctor.
welcome back. Can you still hear me? So we are back to our lecture, topic 4, part 2. Do you have any questions so far? Wow, macam belajar kat outer space dah. Oh, betul lah. Kan Syafiqah? Yes. Do you have any question?
No, doktor.
Betul lah. Afsar, macam belajar kat outer space lah. Lepas ni kita boleh lah cakap pasal reaction in X1 pula XN by Elon Musk. Apa reaction dia dalam tu kan? Ada siapa tahu? So kita boleh gunalah kita punya background outer space ni. Yeah, because we want to go to Mars. Okay, so I'm going to proceed with the new sharing PowerPoint because we are going to do our exercise relating to topic 4. So it's a little bit lagging from my side here, so bear with me a little bit. I'm going to share my other PowerPoint. You know why it's lagging? Because I have lots of writing and it uses lots of images memory. So therefore, my laptop is working really, really hard at the moment. So give me a while. I'm going to open the PowerPoint first, which I should have opened it earlier. Yes. Badan besar nampak sikit. Ni betul ke? Part tu? Yang ni salah tekan. Tutup muka dulu lah. Duk tengok saya duk terkiar-kiar kat sini. Kita tengok muka yang lagi comel. Let me close one of the PowerPoint. I got 2 PowerPoints here. I'm going to close it first. Tutup. Ambillah borak-borak. Diam aja. Siapa tu tadi? Afsar. Syafiqah dah sampai. Planet mana lah dia dah sampai kan? Syafiqah? Tadi siapa nak yang dipanggil saya jawab soalan? Apa? Apa dia?
Wi-Fi UiTM hari ni macam problem sikit betul?
Kan Wi-Fi UiTM letup dengan saya yang tak Wi-Fi UiTM pun. Tadi pagi I was in UiTM ya. Pun macam slow. I'm not sure whether my laptop ke Wi-Fi pula internet. But anyway, we are in the same boat. Korang pun lagging lambat dengar saya punya percakapan maybe. Okay. Yeah, I'm opening it up and lambat sikit. We're gonna share it. Apalah lambat tunjuk kat sini kan? Jahat pun. Sian kita. Mana dia? Dia tak mau keluar. Ni kot. Okay kat bawah ni. Alright. Can you see now?
Yes.
Yes.
So we have these exercises and examples. ditulis topik 5 and 7. Tak, actually I'm going to pick some of the ni when I did that I put everything in. So I'm going to choose one of the examples from topic 4. Yeah. So before that, I will go to view slide sorter then. I'm going to choose my examples. Since we have done the CSER and also the PFR, so I'm going to choose one example for the CSER. We have done a very simple example last week, was no challenge at all, but this time just going to show you. I'm not going to ask you to go to your breakout room, but you are going to see the one of the example in CSER and also the PFR. And that PFR is the determination of the design volume for the PFR using the numerical integration method. It's just showing, but you'll see how I do it. I'm going to decide which example saya nak pilih. Kejap ya. Okay, let us try 11 for sizing CSE. So if you have your textbook with you, then we are going to try this by using the Lebensspiel plot for the design of a CSTR. With this simple reaction whereby the A produces B in a CSTR, A enters with a molar flow rate of 0.4 moles per liter. Then we use the data collected to calculate the volume necessary to achieve 80% conversion in CSER. Then we want to know the volume of the CSER necessary by using this figure, yeah, with the same conversion, 80%. So these are the data that you get from the experiments in the lab for the gas phase isomerization. Have I done this last week? No, right? I don't think so.
No.
Right? Yes, thank you, Ms. Afsar. Yeah, thank you, Shafika. So we have the collected data of varying X and also the rate of disappearance of the reactant A. So you have the respective minus RA to the respective X. Then okay, that is the basic data that you have. Yeah, since we want to use the Lebensspiel plot, assuming perfectly mixed because the CSTR has D impeller, and the volume formula is simply the FA naught times X over minus RA. So now, having the data that you collect from the experiments, so if you plot the X versus the 1 minus RA, why? Because we have this formula, yeah? V is equivalent to FA naught X over minus RA, yeah? So the 1 minus RA is the y-axis with the change of conversion would be your x-axis, yeah? The FA naught is a constant. So it's a constant, yeah? So you don't need to plot it. But of course, we also plot it with FA naught over minus RA. I think I have it in the next slide, yeah? All right. So when you plot the FA naught over minus RA, with varying X, you get this ascending trend, yeah? According to Lebensspiel plot for a CSTR is simply the area under the curve for that limit from X not equals to 0 to a specific X achieving 80%, yeah? So this 0.8 is 80% of X. So from that limit, initial limit to the maximum limit there of 80%, shaded area under the curve is the integral form, yeah, mathematically defined by the integration. But then for the Levenspiel plot says that if we take the y-axis here, which is the function here, y, which is 8, times the 0.8, which is the rectangular, or it could be the square area, would give you 6.4 meter cube. Yeah, so Levenspiel says simply by taking the whole shaded area would give you the volume for the CSCR. So this is what it means. It says there, the volume for the CSCR according to the Levenspiel area is simply 0.8 times the Y there. So giving the whole shaded area, right? So knowing that now to achieve 80%, we need 6,400 liter. So how do we design the reactor? Of course, with the cylindrical, we know that the volume is defined as the pi r squared times h, or you define it as diameter. So if you have a specific diameter, how big of the CSCR is going to be based on your defined diameter, you just need to find the h. Yeah. So from this formula, the simple Alhamdulillah. The simple formula will give you DH. So the design height chosen would be the round number to one decimal point, which is 3.6. So if you were to check DH 3.6 times the diameter 1.5 will give you 6.36 meter cube, which is equivalent closely equivalent to the Levenspiel area, which is 6.4 meter cube. Okay? Are you there?
Yes.
Yes.
Right. So that is the volume for the CSDR. We'll go to the other example. If you were to do that in PFR, I'm not sure whether I have that. I'm going to go back to my slide sorter. Okay, let me choose this example. This is again another example for CSCR. You don't use the Levenspiel plot, but you can solve for the volume knowing, I'm going to change my pen color, light blue, knowing specific volume, knowing decay, knowing the molar flow rate, knowing the initial concentration. So you write all the information there. So you have the CSCR with the inlet and outlet, initial FA naught, then concentration initial, the volume, the K, which means it's isothermal. Then your assumption is steady state and perfectly mixed. Then you simplify the mole balance equation, and this is your final equation for the volume. Yeah. Now, since it also, does it say it's first order? Let me see. No. But if we assume this is elementary, so 1 mole of A produces 1 mole of B, then we can say first order reaction. So what is the conversion? Yeah. What is the conversion having this initial molar flow rate, initial concentration, with that volume and with that K, yeah? So from that equation, simply find the X, rearrange, and this is done in a CSTR. If there is no change of phase, then we can say that the volume is constant. Insert it in, and that is your final equation for the x, and simply plug in the information and you get the x. All right. Any question? Now, I'm going to go to in your textbook, we have a comparison between what if you calculate the volume if you're using CSCR or PFR. Yeah, so it's a very good example. I don't remember which example, but it gives you an idea that the CSCR volume is bigger than the PFR with the same X and also FA naught. So let us go to the other example here. I'm going to go to an example which is related to today's lecture straight first, which is this one. Now, if you were to find the design volume for a plug flow reactor using the numerical integration method, then having the data of X and rate of disappearance, if we were to choose trapezoidal, then it gives you 2 point. The volume of the PFR is 3.52. If 3 point, let's say this is 3 point, then the volume will give you 2.28 meter cube. Yeah. With 2 point, it gives you 3.52. With 3 point, it gives you 2.28 meter cube. If you use the 4 points, 4 points, which is the 1/8 rule, then it will not help you to calculate the volume, because you know the rule that we have to have a distributed equally segment for 4 points, meaning 3 segments. Unfortunately, having that H at that point 0.27, and the third point is x2 at 0.52 conversion, x at 54% conversion. Unfortunately, we don't have that x at 0.27. No, we don't have that. And 0.54, we don't have that. So we cannot use the graphical method to get our fx at that 27% of conversion and 54% of conversion. So therefore, we cannot use this 1/8 rule, if we were to find the design volume. But for the 5-point quadrature, yes, we can for here at 20%, 40%, 60%, and 80%. Then it tallies with the sampling data. So from the numerical integration method, the volume using the 5-point quadrature is 2.16. Remember, 2 point, 3.52, 3 points, 2.28, and 5 points, 2.16. So if you notice, as it goes to the bigger point from 3 points to 5 points, then the volume is quite close to each other. But the most accurate one is with the 5-point quadrature rule, Okay, do you have any question? I just show first. You may have to try yourself, next time. Do you have any question? Maybe you want to ask, if you were to decide the design volume, which method would you use? The answer would be, if you are to use the numerical method, which method?
5-point quadrature.
Ya, Afsar, buka video sikit nak tengok. Mari kita nak sama-sama pergi angkasa. Afsar. Yeay. Kenapa pergi seorang? Kenapa pergi seorang je? Kenapa tak ada muka I? Kenapa tak ada kat situ? Kenapa tak di Syafiqah ada? Azal lah. Oh, jap. Kenapa tak ada? Kenapa?
Mungkin sebab
Haji
saya
dia nak
bumi.
pergi seorang-seorang.
Saya
You
dekat
nampak
bumi.
Dekat bumi. You can... You nampak sebelah-sebelah dalam skrin you. I nampak you seorang je. Tadi kenapa I nampak Syafiqah dengan I sama-sama? Heran lah. Dia jaga betul lah Muslim friendly. Muslim friendly channel. Okay. Alright, just kidding. So Afsar, what is your answer?
5 point quadrature.
Yeah, because?
Sebab tu dalam latihan ni dapat jawapan yang paling tepat.
Paling tepat sebab? Mana you tahu 2.16 paling tepat? Tak salah. Kerja banyak nak kira banyak point.
Sebab dia pakai point genap-genap 0.24.
Dia pakai point genap-genap. Okay, genap-genap tu because we choose genap-genap because that is the rule of the numerical Simpsons punya formula there. There is numerical punya formula for genap. Then we follow the 424242. Right? But why the 5.2 would, how sure are you this would be the most accurate in comparison to 3.52 tadi? Tata 3.52. Kira 2 kali cukup Berapa nak kira sampai 5 kali? Tengok ni Buat kerja penat je. Bila nak habis jawab exam?
Sebab bila lagi kecil dia punya gap autograph tu lagi accurate calculation.
Yes, very good. That's the answer that we want to read. Patutlah pula. That's the answer that we want to hear from you. Very good. Mr. Afsar. Okay, you nampak screen you kita sebelah-sebelah ke? You seorang je? You nampak I?
Saya nampak medium juga.
You nampak sebelah-sebelah? Sebelah-sebelah ke apa?
Tak.
Oh, cuma ada Syafiqah tadi boleh. Hairan. Okay, thank you Mr. Afsar. I nak testing tengok. Is it Muslim friendly? So kita call upon Syafiqah. Okay, come on Syafiqah. Switch on your camera. Tengok apa jadi.
Sebab duduk kat angkasa tu doktor.
Dia dah sampai angkasa. Okay, kita panggil orang lain. Kita panggil another lady. Okay. Shadiana. Nur Shadiana.
Ya, saya dah.
Buka kamera you. Allah, satu juga. Wah, kan? Tak dapat.
Nampak ke doktor?
Seorang yang datang gelar ini. Satu juga. Tak kecil lah. Sorry, nak testing je. Satu juga. Okay. So, thank you Syahdiana kerana sudi untuk open your camera. So, I'm going to... Dua. Yes. Muslim friendly. Muslim friendly Microsoft Teams. You nampak dua tak? Pernah nampak tak?
Tak nampak pun doktor.
Tak nampak pula. Sekejap, saya paste kat sini. Tak nampak dua. I nampak dua you. Ya. Tadi Afsar tak nampak dua. Lagging betul lah. Sebabkan lagging ni kita leisure-leisure sekejap. Nampak sangat.
Doktor pin doktor punya ni video.
Saya pin sendiri. Oh, kena pin baru boleh keluar dua
Tak pasti.
Betul lah kot. Sekejap, saya nak pin Afsar. Pin Afsar. Where is he now? Gone. Sini. Betul lah. Tadi saya tak pin, keluar pin pula. Nampak dua dah. Alright, so now we're gonna go to the next example. Tak sure lah bila lagging macam ni. Aduh. Now. Sorry ya, bila lagging macam ni tak sure. I am looking for an example which I have here yang I compare between the PFR and also the CSR. Somehow maybe I don't have that. Let me see. For those people who got the textbook, please have a look at which example yang dia compare PFR dengan CSR, yeah? So you may mention it here so that all of you could try it also at your home together, yeah? So I'm gonna go to this PFR example now. Nampak sikit. So can you see this slide PFR example? Nampak Now, so it says there for a PFR reactor, knowing sebenarnya bila you write your own solution, of course it will be, I know you like to skip all those small balance equation, yeah. But then it will be a very good practice if you do that. Now, we have the entering volumetric flow rate at specific 6 meter cube per minute, the entering, and then calculate the volume when it reaches 70% conversion, knowing the K, yeah? So with the assumption, so I wrote from your mole balance, then you have this mole balance simplified equation. You want to find volume, so you integrate from volume 1 to volume 2. Then the F, the K is constant because isothermal. Then we have the CA formula when we have no change of volume. Yeah, sorry, no change of volume. This is for the mathematical changes of sub-volume to the del V, yeah, for your derivatives. All right. Here we are replacing the CA by this equation, assumption number 8. Then you simplify the CA naught, and the final equation would be that equation. I've shown that last week, but simply that on this slide I showed to you how do I solve my calculus, yeah, the integration of the 1 over 1 minus x, yeah. So those are the mathematical steps, finally giving me the ln of 1 over 1 minus x. And finally, you got your V. Okay. That is just to show you the mathematical functions. The next one is again, deriving the equation for the reactor volume, determine the reactor volume necessary for K, then for the volumetric flow rate, and we have volumetric flow rate to reduce the exiting concentration to 10%. So the problem statement is here, the exiting concentration is only 10%, which means 0.1 times the initial concentration. And the K is given, yeah, and the volumetric flow rate is 10 cubic decimeter per minute. So that is the volumetric flow rate. So you have the basic equation for the flow reactor system. That is the basic equation. Simply solve it by using all the assumptions. Yeah, in this case, the volumetric flow rate is a constant value, so you don't integrate it, simply 1 over FA dF. Then it's simply ln FA, because we have 1 over FA there, ln FA from FA naught to FA. Simply simplify that equation, and knowing CA naught and CA, and substitute the value, giving you the volume. Yeah. So how do you know your CA naught? Is it given? Let us read. Determine the reactor volume necessary to reduce the exiting concentration to 10% of the entering concentration when the volumetric flow rate. Okay, so we have this ln CA naught over CA, right? Let me see. So CA is simply the FA over the volumetric flow rate initial. Mana saya nak cari CA dia? Tengah duk tengok balik apa saya tulis ni. Apa susah formula dah tulis dah kan. That is the thing that we know already. Yeah? CA is simply 0.1 times CA naught. So if you know CA naught, then you can know your CA, right? If you know your CA naught. Do you know your CA naught here? Let me check. Do I know my CA naught here? Is it given somewhere? Mana CA naught saya? Is it given anywhere? Tengok sikit sebelum tu. Kamu pun diam ah? Saya pun diam.
Doktor you simplifikan yang CA tu. Dekat yang equation last tu kan ada CA naught over CA kan. Yang CA tu equals to 0.1 CA naught kan. Nanti potong-potong.
Adai. Petang-petang otak pun dah lembab. Betul. Betul lah, saya tengok pun macam pandang. Ya, pasal otak tak jalan ni. Very good, excellent. It's just a very simple mathematics. So simply substitute 0.1 CA0, then you can cancel out. So 1 over 0.1, right? Betul tak? Thank you. Siapa yang cakap tadi? You're my saver for today. Siapa tadi?
Saya.
Siapa? Karya, tolong buka you punya muka. Tak aci, tak nak buka video. Sekejap ya. Alright, so I will share this exercise form later on. Yeah, hi Karya. So I'm gonna unpin Mr. Akasha, Mr. Afsar here. Mana dia? Saya nak nampak muka dia dengan saya je. Unpin. Okay Karya. Cepat Karya. Hai Karya. Okay, thank you. So masa saya kena pin you lah. Jom kita pergi angkasa kejap ya. Karya. Ni nama you kat bawah. Nurul Karya. Nurul Karya. Okay, pin. Kenapa pin dua orang pula ni? Alah. Tak dapatlah Karya kita pergi angkasa, tak jadi. Laptop saya pun slow lah. Dia kena pin ni saya ke? Tak juga. Dah tak edit lah awak. Ambil gambar. Sorry tak edit. Alright, so while waiting for that, we are going to go to other examples. We got 10 more minutes. Okay, basically saya nak cover example yang saya dah buat kat sini. Kita cari example lain. Now. Simple sangat Maybe this one. Pun simple juga. Soalan dia panjang. Okay, kita tunjuk je. So it is desired, can you see that? It is desired to design CSCR to produce 200 million pounds of ethylene glycol per year by hydrolyzing ethylene oxide. Therefore, before the design can be carried out, necessary to perform and analyze a batch reactor to determine this is a batch reactor problem, which is the simplest problem of all. And it's done isothermally to determine the rate constant. Yeah, so you have done that as your assignment. At high temperatures, there is a significant byproduct formation, while at temperatures below 40, the reaction does not proceed at a significant rate. Consequently, a temperature of 55 has been chosen. Before, the water is usually present in excess. So it says there, the water is, because, not before, the water is usually present in excess, its concentration may be considered constant during the course of reaction. So in the real life, people will know, no one will tell you this, yeah? You have to know this, alhamdulillah, on your own, yeah? When it's in excess, then we consider for that, simplifying the equation, is considered to be constant. So it's a first order ethylene oxide. No one also will tell this. You have to determine yourself. So it's a first order given from this question. So the question would be, we have these 2 molar of ethylene oxide in water mixed with 500 milliliter of water containing 0.9 weight% of sulfuric acid as catalyst. The temperature was maintained 55. The concentration of ethylene glycol was recorded at a function of time. So I just made my own question, yeah, just to initiate your thinking, okay? How to write the expression, what would be the problem statement, what are the assumptions used. It's a first order, you write it, then you want to find the C for the reactant, having all the assumptions. So this is what you do. I think you have done this also by using the linear curve, then you can determine your K there, right? So you have done that. Okay, the rest would be solving the mathematical equations by using the stoichiometric table for a batch reactor system. So you may try this at home as well. At home pun, you may try this. Example 4.1 in Fogler. Once you have that, then you can determine your K. Now, inilah kot. Yes, done in parallel. Tiga yang comparison between the volume of the CSCR and also the volume of the PFR. Yes, this is the one. Itulah saya skip sangat. But anyway, this example 4.2, I remember I have this. Yeah. If you, with the same X and the same FA naught, I guess so, must be in the question, find the volume of the CSCR. Then you also find the volume for the, that is two parallel. So that is different topic, yeah? Different topic. Belum sampai lagi topik ni. But anyway, this volume for this example 4.2 giving you for a CSCR 197.3. And we did the same condition of 4.2 and compare it with the plug flow reactor. And this is what we got, yeah. For a 2 point, it's 3.52. For a 5 point, it's 2.16 meter cube. So meaning for a plug flow reactor, it only needs 2.16 meter cube if you choose a 5-point quadrature rule. But for a CSTR, it needs at least, sorry, the lagging of the slide, at least 197. All right, so this is the proven example with the same condition. It needs more volume by using the CSR in comparison with the plug flow reactor. All right. Okay, you may try this at your own pace. Try the numerical method and also the integral method, the Levenspiel plot, the direct algebraic form method, yeah, for batch or the CSCR. All right. So do you have any questions so far? So I will share this slide for the exercise. I will check out the topic 5 and 7 and share with you the topic earlier and also until topic 4. But this is mainly topic 4 are here. Yeah, I will share that. But I want you to try first at your own pace. Yeah, I will do that a little bit later. Yeah. So I guess this is now already 5:50. So we will adjourn our class at 5:50. I'm so sorry about the lagging of the slide, but I hope you now can see how to solve for the volume of PFR and CSTR, then the batch reactor system earlier from our previous class and so on. It's not so difficult, but it just need practice. Okay, so we will start with the new topic in the lesson 2, week 5, when we meet again on Thursday. All right, so the class is adjourned. I would like to wish you selamat berbuka puasa for today and have a nice day ahead. Yeah, take care, because I just came back from UiTM tadi in the morning. I went to the office and I wanted to call one of the officers who sent me a letter like 10 days ago. And now when I went to the office and wanted to talk to him, and he was told by his colleague that he is now COVID-19 positive. Yeah, so the pandemic is not yet decreasing. So please stay safe and take care of yourself wherever you are. Right? For those people who are staying in Selangor, duk college ke apa semua ke, take care. You are not allowed to go out from your campus at the moment, right? So unfortunately, duduklah dalam tu. Okay, even yang dalam campus pun ada staff yang kena COVID dan kena quarantine. Yeah, so please take care of yourself.
Okay, thank you doktor.
You're welcome. Selamat berbuka puasa.
Thank you, Doctor.
Thank you,
You're
Doctor.
welcome.
Thank you, Doctor.
My pleasure.
Doktor.
Selamat
Thank
berbuka.
you, Doctor.
So, jangan pergi pasar Ramadan banyak sangat ya. Selamat buka.
Pergi dah.
Tak pergi dah. So if you see a lot of people, stay away. Alright? Pergi tempat yang paling kurang orang, okay. Stay safe. Okay, Assalamualaikum.